to introduce Akira. He received a PhD from Kyoto University in 1992, and previously, until 14 years ago, he was an associate professor at Hokkaido University in Sapporo, and now he is a professor at the Yukawa Institute, Kyoto University. He has been working on a variety of areas in heavy ion physics, from molecular dynamics for low energy heavy ion collisions to high energy heavy ion collisions. And event simulator JAM, for example, was written by one of his students, Yasushi Nara, and also Akira also worked on lattice gauge theory some years ago. And today he will talk about exploring hadron interactions and bound states with femtoscopy in heavy ion collisions. So please start now.
Asakawa-san, thank you very much for a nice introduction. This is Akira Ohnishi from Yukawa Institute, Kyoto University. And today I'd like to talk about the bound state and femtoscopy on the hadron-hadron interaction and bound state. Okay, and first, after a short introduction, I'd like to first talk about the interaction dependence of the correlation function and the bound state diagnosis by femtoscopy in the second part. And in the third part, I talk about the recently observed or studied correlation functions and their homeworks to heavy ion physics and hadron physics and several perspectives. Okay, it's nothing to say, but of course, the main goal of heavy ion physics, heavy ion collision physics is discovery and elucidating the properties of quark-gluon plasma. That's the main goal. That's not no doubt. But the heavy ion collisions are also used as a playground or tool of various physics, such as the development of dynamical models, such as the viscous hydro and the transporter models and chiral kinetic theories and so on. And the heavy ion collisions are also used as the tool or background playground of physics of extreme conditions or strong field, such as strong magnetic field or the high temperature, high density matter, or the highly anisotropic, isospin anisotropic situation. And one of the areas to be used by to use heavy ion collisions is the hadron physics. Because at the end, the final stage of heavy ion collisions, we have a lot of hadron gases. Then it produces a lot of hadrons at the same time. And we have nearly 4 pi detectors in LHC and RHIC accelerators. And in addition to that, the hadrons are almost statistically. Therefore, the property of the source is well known, relatively well known. Therefore, it's a very good playground for hadron physics. And among the various subjects in hadron physics, I'd like to talk about the hadron-hadron interactions today, because hadron-hadron interactions have a lot of relevance to various physics, such as nuclei or hypernuclei, and meson mass modification in medium, and the exotic hadrons, including TCC or lambda 1405 hadron molecule and dibaryon. These are all categorized as exotic hadrons. And the hyperon nucleon and hyperon nucleon interactions are very important to solve the hyperon puzzle in neutron stars. And it indirectly related to the QCD phase diagram at the finite density. We may have a first order phase boundary, or there's no first order phase boundary or critical point, or nobody knows yet. But we can probe the heavy ion collisions to probe this area directly, but indirectly through the hadron-hadron interaction, we can tackle this QCD phase junction. Therefore, hadron-hadron interactions is one of the central issues in hadron physics, I believe. And for example, the attractive repulsive, which is not known for many of the hadron-hadron interactions, and how strong to be bound or not to be bound. Those are not known. And recently, the femtoscopy is known to be very important and useful to constrain the hadron-hadron interactions. And correlation function, I believe that it is not necessary to explain what is the correlation function, particle momentum correlation function, but the correlation function is defined as the two-particle detection probability normalized by the single particle detection probabilities product. And it is known to be represented as the product convolution of the source function and wave function squared. Okay. And usual way, standard way to use the correlation function is to constrain or extract the source size, HBT effect. And when we have two pion correlation functions, then it becomes maximum at their momentum and it goes down quickly. And the half width at maximum is proportional to the 1/, source size. And by this way, the Humphrey run and twist measured the radius of the series A 60, 70 years ago. And that is very close to the most recent observation by just 10% error or something. But in addition to this source size, it also depends on the wave function squared. And if we know the source function, then we can extract the information of the wave function or the interaction wave function. It depends on the interaction. Therefore, we can access the hadron-hadron interaction. And the first person who said that we can access the hadron-hadron interactions is maybe Lednicky and Lyuboshits in 1982. And after that, many people try to extract the information or conform the information using this correlation function. This is one of the examples. The horizontal axis is the one of the scattering lengths for the lambda-lambda interaction. And the vertical axis is the effective range. And by using the Hebbian collision data of correlation function, we guess that the interaction is very likely to be around here. But at that time, the data is not very small, than the allowed area is this one. Okay. And later on, the RHIC people constrained the region in a better way. Okay. And this way is known to work well, at least for the lambda p correlation function. The prediction was given by using the known lambda p interactions by Wang and Pratt in 1999. And this lambda p correlation function was measured by the star collaboration. And before that, the MINDS and HADES and other experimental facility measured lambda p correlation function. But this star collaborations one is a better one than before. And the correlation function goes like this. And this is a non-identical particle. Therefore, from quantum statistics, the correlation function should be one, just one. The enhancement comes from the attractive interaction between nucleon and lambda. This correlation function is well reproduced by the known lambda p interactions. And it is also possible to extract the interaction parameters such as scattering lengths from this correlation function data, and it reproduces the known n lambda interaction. And later on, RHIC collaboration measured the lambda p correlation functions very precisely, and we have a lot of data points like this. And it also well reproduced the cusp at the sigma 0 proton and the sigma plus neutron threshold. And this cusp height is related to the strength of the lambda and sigma n coupling. And it well reproduced by the chiral EFT effective interactions from NLO19. Okay. Therefore, for at least for p lambda correlation function that is well described by known n lambda interactions and extracted scattering parameters, scattering length and effective range probably, these scattering parameters are consistent with those in known interactions. Therefore, correlation function to interaction works. Therefore, the correlation function contains information on hadron-hadron interaction, and it is also possible to guess the existence of a bound state by using its correlation function, as I explain later. In addition to confirmation of proposed hadron-hadron interaction, recent data seem to distinguish models and to require improvements in present hadron theory. And that is the main subject of this talk. But before proceeding to the real contents, let me excuse something. I know that the state-of-the-art femtoscopy of source size and shape is well parameterized, and it's the correlation function, the source size for the longitudinal and the side and out is well extracted by using a 3D Koonin-Pratt parameterization exists. But just for 1 hour, please forget the 3D source functions, the serious flow effects, and so on for 1 hour. During the talk, please forget, but you can ask me after the talk. Let's discuss. We will mainly use a spherical Gaussian source function, the simplest one. A statistic is low for identified flavor hadron pairs, and only one-dimensional correlation function is shown up to now. For example, in the case of the D minus proton correlation function, error bar looks like very large, and the data points are small, and we cannot bin these events to the MT bins or something like that. It's not possible yet. Therefore, we have to rely on one-dimensional spherical source function. Okay. Let me proceed. And first, I'd like to explain the interaction dependence of the correlation functions. Okay. And as you know, the single particle emission momentum distribution is given as the integral of a source function, position, space-time position, and their momentum. And the two-particle momentum correlation function is defined as the ratio of the probability, detecting probability product. And it is known to be explained, written as the source function and the wave function squared. For spherical static source and for non-identical particles, and we assume that only the S wave part is modified by the strong induction, and we ignore Coulomb. Then this correlation function is given as 1 plus the wave function enhancement from the free case with the weight factor of the source function. Okay, and this Q is the relative momentum, and many experiments use K star instead of Q. But let me use just Q, momentum transfer, or the relative momentum. Okay, this is the basic equation proposed by Koonin and Pratt, and Lednicky and Lyuboshits derived an analytic formula given in the next slide. Yeah, this Lednicky-Lyuboshits formula is very, very useful. And they have assumed that the asymptotic wave function can be used in the Koonin-Pratt formula here. And for non-identical particle and short-range interaction and no Coulomb and the single channel calculation and something like that. Then by using this kind of the asymptotic wave function, the correlation function is known to be given as a known function F1, F2, F3, something like that, 1, 2, 3. and there's the relative momentum, and the scattering amplitude F. F is proportional to the 1 cotangent delta minus IQ inverse. Okay, and therefore it means that this phase shift delta is parameterized by the scattering length and effective range. And we also have the Gaussian source size R. Therefore, by using this scattering length A0, effective range are effective, and the source size R, then you can draw the correlation function CQ. And therefore, interaction dependence, or more precisely, the scattering length dependence of the correlation function is easily drawn. Okay. In the case of the repulsive interaction, and it's clear, CQ is suppressed. And in the case of the attractive interaction, the wave function grows rapidly at small radius with attraction. Then CQ is enhanced for small source, irrespective to the source size. Source size. Oh no. For small source size, then the wave function is enhanced and the correlation function is enhanced. And this kind of enhancement is well observed in experiment. For pig's eye, this is Alice data in 2019, and we see a strong enhancement above the pure Coulomb attraction. Also, in the case of the pk minus correlation function, we have a lot of data points with small error bars, which is the best record for the pk minus scattering. And it is also enhanced compared with the pure Coulomb correlation function. Okay, and P phi meson is known to be maybe mass shifted in nuclear medium. Therefore, the P phi attraction is observed probably for the first time directly via the correlation function. And P omega minus. Omega is SSS baryon, and it is also enhanced at low momentum above the pure Coulomb case. And P and D meson, C bar D quarks, and it is also enhanced compared with a pure Coulomb correlation function. These are all observed in these 7 years. Okay. And there are also there are a lot of theoretical works, including ours and the Chinese group, and there's the Poland group, and German, and Iran, and something like that. Okay, there are a lot of works. And next thing is for small source, it's easy. When we have attractions, then a strong correlation function is enhanced. Then, but in the case of the source size becomes large, I mean that the A0, when it becomes comparable to the A0, it shows somewhat different behavior. Without a bound state, in our parameterization, negative A0 scattering length means that there is no bound state. In that case, the correlation function is still positive, enhanced from 1. But when we have a bound state, negative A0 case, then the correlation function may be suppressed at small relative momentum. And why the correlation function is suppressed when there is a bound state? And do we really see enhanced correlation function for small size and suppressed correlation function for larger source size, and where there is a bound state? Okay, that is one of the main subjects of this talk. Bound state diagnosis by femtoscopy. Let me talk a little about the low energy wave function and phase shift. Okay, we consider the case of the wave function times the QR, and that this is just one-dimensional wave function. which satisfies one-dimensional Schrödinger equation. And the asymptotic wave function of this U is sine QR plus delta. Delta is a phase shift. And this delta is, roughly speaking, minus A0Q. Therefore, when we substitute this minus A0Q to this delta, then we find that the sine Q times R minus A0. Therefore, the asymptotic wave function, or the asymptotic wave function, has to have a node at A0. And when A0 is positive, there is a node of the scattering wave function at finite R. But when A0 is negative, then the wave function does not have the node in the small r region. This is the difference. And the wave function grows at small r for attractive interaction. But when there is a bound state, there is a node at scattering length. And when the scattering length is smaller than the source size, then within this source, then the wave function has a node. Then it is suppressed on average. Therefore, the correlation function is suppressed for large source comparable to the scattering length or larger. This situation is well summarized in a bird's eye view of the correlation function. The horizontal axis is the relative momentum times the source size QR, and the horizontal axis is source size over scattering length R over A0. Then when there is no bound state, then the correlation function is always enhanced from 1. But when there is a bound state, then when R and A0 becomes compatible, then the correlation function is suppressed. This is the situation. And with Coulomb potential, Coulomb attraction, then at very small relative momentum, then the wave function and the correlation function are enhanced. But the dip appears, okay? Then do we really see this kind of dip at the large source and the enhancement at the small source? It's just is a question. And we really see, before that, this figure is drawn within the Lednicky-Lyuboshits formula, and under the assumption that the effective range is 0. You may think that these are unrealistic, but let me compare it with a realistic correlation function. This figure is drawn using the HAL-QCD lattice baryon potential for nucleon omega for j equal 2, where the scattering length is 3.4 Fermi. Okay, and the Coulomb is interacted, and the couple channel effect is also included. No, this is the NOmega. There is no couple channel. Okay, but anyway, this is the result with realistic interaction, and the qualitative features are the same. Okay, well, of course, it's better to draw in a same color band scale from 0 to 2. Then, anyway, this is green, means that it is just 1, and there is a dip, which is blue. Okay. Therefore, the qualitative feature remains with realistic interactions from the Lednicky-Lyuboshits analytic model formula, and it also applies to the couple channel effects, which we do not show here, but it is true. Therefore, we expect such kind of source size dependence of the correlation function. And such kind of bound state dip is rarely observed in experiment. And for example, in the case of K minus P and P omega correlation function, let me start from the P omega correlation function. And Alice collaboration observed the p omega correlation function from high multiplicity events in pp, 0.17% centrality, and therefore the source size is small, at the order of 1 femtometer. Then we observe very strong enhancement compared with the pure Coulomb case. Okay, but when we go to the gold collisions, then this correlation function is suppressed at small q, which corresponds to this case because the scattering length is 3 or 4 femtometer, which corresponds to the size of the heavy collision source. In this case, they assume that it is 2.5 femtometer. Okay. Anyway, which is comparable. And in the case of p omega, lattice QCD calculation predicts that there is a bound state, which is shallow, but there is a bound state. And in that case, we see this kind of dip. This may not be very convincing because the error bar is large. But in the case of K-P, the data is very, very beautiful. In the case of the PP collisions, the high multiplicity event, then the correlation function is enhanced at small relative momentum. But when we go to the lead-lead collisions, then the correlation function has a very clear dip. And scattering parameters such as the scattering length is very good, which is comparable to the C delta data, which is a Koenig atom experiment. Therefore, when we have a bound state, then we have a dip for large size and just enhancement for small size. That is already observed.
Let me interrupt a little bit.
Yes.
There's a chat question. Would you explain the physical meaning of the correlation function for a new person in this field? For example, what is the reason behind the introduced so-called source function? Do you think you have to answer this question, or you can answer at the end of your talk?
Wait a minute. What is the real explain the physical meaning of the correlation function for a new person?
Yeah.
In this field. What is the reason behind to introduce the source?
I think it's a rather hard question.
Yes, let me explain later. Is it okay, Asuka-san?
Yes, that's okay. And also, Tianmin raised hand.
Tianmin and Jürgen.
And on the Jürgen. From
there's
a sorry, I forgot. I accidentally hit it. Forget it. Sorry about this.
Okay. From Jürgen.
There's a cusp here. Okay.
Cusp at 50 MeV. What is that?
For 50 MeV, okay. This is the cusp, which couples at the threshold of K0 bar neutron. And K-P and the K0 bar neutron has a coupling between, and this cusp is observed. And but in the case of the gold, then lead, then the couple channel effect is strongly suppressed for large source. And therefore don't see the clear cusp. And
okay, there's another chat question, but I don't think this is an urgent question.
Okay.
So please go ahead.
Okay. Thank you. Okay. But maybe it's better to open the chat here. Okay. Okay. Let me proceed. Okay. And let me explain again about the NOmega dibaryon state, and as in also in the realistic model interaction calculations, correlation function is enhanced for small size, and the correlation function has a dip for a large size. which really corresponds to the Lednicky-Lyuboshits formula predict. And these really correspond to the experimental data. It also applies to P minus K correlation function, PK minus correlation function. For small size, we have a dip. We observe a dip. In a case of the coupled channel effect is introduced in a simple way, but when we choose the coupled channel effect little, then we can reproduce the PP correlation function data. And this is another resonance lambda 1520, which is in a D wave. Therefore, we cannot reproduce this one from a S wave calculation, but we can introduce it in a separated way. When the source size is large, the coupled channel effect becomes smaller and the dip becomes clear. Okay. And which is really observed in lead-lead collisions as well as the gold-gold collisions from Star and Alice. Therefore, Star and Alice data show a dip at small q, and this shows that there is a bound state which is known as the lambda 1405, known as the K minus P or K bar nucleon bound state. Okay, and the scattering length extracted from the K minus P correlation function is minus 0.91 plus with the imaginary part of 0.92, something like that. Okay, and this one is comparable to the Siddhartha data, which is a dedicated experiment of to extract this scattering length using the Keonic atom. The Siddhartha data is minus 0.5065 plus 0.81 I. Okay, this is the Siddhartha data, and this is the Alice data, whose value is comparable to the Siddhartha one, and the size of the error is similar to the systematic error is larger, but the statistical error is smaller for Alice. So it's very nice to extract the hadron scattering parameter from heavy-ion collisions. Okay. Let me go to another case, which is marginal. D minus P correlation function. D is the first. D minus P is the first measurement of the two-body scattering involving charm hadrons. Okay, the data error bar is still large, but which shows enhancement from the pure Coulomb curve, blue one, and there seems to show some dip and go back to one. This is the result, and it is they are compared with the theoretical predictions of Heidenbauer and Lutz. This one? No. Oh, modified one is Heidenbauer's one is this, and Fontoura and Hoffman and Lutz, they show some suppressed correlation function, but the Yamaguchi, Okoda, Yasui, Osaka result is very enhanced. And there becomes the error bar, chi-square is the smallest for Yamaguchi et al. And the next one is Heidenbauer's one. And the original Heidenbauer's parameterization says that it is repulsive and the chi-square is worse. But when he introduced additional attractions, then it becomes closer to this curve. And I have to confess that the Heidenbauer is one of the co-author of this paper. He introduced it later. I hope that Johan is not in the audience. Okay, and to be bound or not to be bound. And when there is a bound state, the correlation function shows interesting dependence on source size and the relative momentum. When the source size is not very large, then even though we may have some dip, And when the source size is big, then it is a suppressed behavior, as already mentioned. And the data looks like this curve, and we may have a bound state if it is bound. This is the first weakly decaying pentacork state, which is very good, great, and it's too interesting to believe. But the best fit parameter of this equation function gives a scattering parameter in the bound region. Therefore, there may be a bound state. And this is by itself, it's great, I believe. We may have a bound state. And before that, this is the first measurement of the hadron scattering involving charm. In addition to that, it's very interesting for me. People believe that the chiral symmetry, from chiral symmetry, the pseudo-scalar meson and baryon interaction is dominated by vector exchange, so-called the Weinberg-Tomozawa interaction, which comes from the chiral symmetry itself, and there is no parameter for this Weinberg-Tomozawa interaction. Therefore, people believe that this is the leading order and the most dominant one. And it is interesting to find that Weinberg-Tomozawa interaction is generally repulsive in exotic channels. Therefore, in the case of the D-P channel, that is the, how to say, manifestly exotic channel, C bar UD pentaquark state. Therefore, it is in exotic channel. Therefore, people believe that the D-P interaction is repulsive, as most of the works predicted. Then what is necessary? With heavy quarks, pseudo-scalar meson and vector meson masses become closer. For example, in the case of the charmed meson D and D star, then the mass difference is just 145 MeV. In the case of strange meson, then the K and K star mass difference is over 300 or 400, 350 MeV or something like that. But in the case of charm, D and D star mass difference is almost the prime mass. Therefore, the vector meson pseudo-scalar meson coupling becomes strong, and the two pion exchange becomes much more important. And then the two pion exchange is generally attractive, and the attractive interaction appears like this. This is the thing which the correlation function tells. And this charmed pentaquark may exist as a bound state, and femtoscopy may cause a change of the paradigm in hadron effects, I think. Okay, let me check that the case without a bound state. Lambda and n xi seem to be unbound from lattice C calculation. And therefore, there is no H particle as a bound state. And from PP collisions, the lambda correlation function looks like this. When there is a bound state, then this suppression comes from the HBT effect, quantum statistics. Okay. When we go to the goal collisions, then the results are very similar. At zero momentum, the extracted one may be 0.85, which is also true for the goal data. P xi minus. It may be expected that there is bound state of P xi minus, and of course the P xi atom should exist, but there is no bound state from the strong interaction. And the correlation function from PP looks like this, strongly enhanced from the Coulomb, pure Coulomb case. And for the goal data is not yet very clean and preliminary still. But even in the case of these larger data, the correlation function seems to show enhancement. There is no dip. Therefore, the enhancement is suppressed for larger sources, but it is still enhanced. It is consistent with the case LL formula without a bound state. Okay. Therefore, what I explained is the source size dependence of the correlation function seems to be very useful to deduce the existence or the non-existence of a bound state. And this provides a good motivation, but it is not a proof, I'm afraid. At the ASIC, Asian Triangle Heavier Collision Conference, and there was a question that is, from the correlation function, you can guess the existence of a bound state. Then it is not necessary to find invariant mass spectrum peak. That's a very tough work. But I'm afraid that this is not a proof, but just suggestion or give motivation. For the confirmation of new bound states, and invariant mass peak with significance of 5 to 7 sigma needs to be found in experiment directly. That is the thing which I guess. And I think that many experiments experimenters agree with this opinion. Okay. Okay, let me go to, I have 1 hour talk plus 30 minutes discussion. Is it okay, Asakawa-san?
Yes, that's right.
Okay. Okay, I have 20 minutes. Okay, let me proceed to some recently observed or studied correlation functions and homeworks to hadron physics and heavy ion physics and some perspectives. Okay, exotic hadrons, including CC bar, CC or C bar, C bar, are the main playground of exotic hadron physics. For example, the X3872, this is the first observed exotic hadron at Bell. And this is the chip psi. And after that, we Bell collaboration observed a small peak. And this is 3872. This is not, this is exotic, and they did not know its properties, and they named it X. Okay. After that, there are a lot of exotic hadrons observed, and some of them are called Y, and some of them are called Z. And Belle and CDF and Babar and LHCb and CMS and the BESS 3. And this BESS is not the beam energy scan, but the Beijing spectrometer. Okay. Therefore, the Chinese people want to collaborate with the Beijing people by beam energy scan program and the Beijing spectrometer program. That's interesting. And the charmed pentacoque is observed recently by the LHCb collaboration. And the doubly charmed tetracoque state, TCC, was observed last year by LHCb. This is TCC, and which is shows a very clear peak. And the thresholds are drawn by a green and magenta line. And it seems that it is really below the lowest threshold. And this is the bound state. And for these exotic hadrons, the main question is the structure of exotic hadrons, compact multicoque states or the hadronic molecules. In the case of TCC, that's a CC Q-bar. And many people believe that this is really a tetracoque. Because in the case of U-bar, D-bar, then this is isospin that can form a isosinglet dicoque pair, and which is called a good dicoque. And good dicoque gains energy. It's better to have this dicoque rather than combining the D bar C and U bar C, something like that. And in the case of the X bar, X3872, then it can make a D star or something like that. and that is a hadronic molecule, whereas a color singlet hadron forms a molecule. And the way to distinguish the compact molecule state and the hadronic molecules is always desired in exotic hadron physics. And I think that we can partly answer this question by using the correlation function. And let me proceed a little more. TCC is believed to be a compact tetraquark state because of the good anti-dipole gains energy. In the case of X3872, then a CCBA component is known to be important from experimental point of view. Therefore, CCBA component is necessary, but the 4-quark, the molecule type component is also necessary to explain the large yield in lead collisions. CMS collaboration observed the ratio of the X3872 with respect to the J psi 2s state, normal hadron state. And the large yield from heavy-ion collision compared to the PP collision is a kind of signature of the extended molecule as exit collaboration predicted. And the hadronic molecule condition may be summarized like this, and appears around, I'm sorry, it is shifted.
That's okay. No problem.
Okay, no problem. Okay. And the hadronic molecule condition is that it should appear around the threshold. It's okay. TCC is just 270 keV below the D0 D star plus threshold. And the X3872 is just 40 keV below the D0 D0 star bar threshold. And this is okay. And when that is really a molecule, then the binding radius of the wave function should be inversely proportional to the square root of the binding energy. And when we have a large size, then we expect that the yield in heavy-ion collision becomes large, and which is not measured yet. And the most important thing is that this state is described by the hadron-hadron interaction extracted from the correlation function. That is the point. How can we access the hadron-hadron interaction with charm? That is a Femtoscopy, as I already explained. And therefore, DD star and DD star bar correlation functions are predicted by Kamiya, Hyodo, and Ohnishi. And Alice round 3 can measure the correlation functions of DD star and DD star bar. And this is still in the stage of the LOI, letter of intent, but I hope that they measure the DD star and DD star bar correlation functions. And in order to make a prediction for this correlation function, we introduce a model interaction. Strength is fitted to the pole mass of the TCC and the X3872. And the spin dependence is introduced as the simplest one. Anyway, this is a first work, therefore, this is how to say, minimal requirement. And we have introduced the pion range interaction because the D and D star can exchange pion to the same channel, but of course the momentum is changed. It's okay. Let me show the result. In the case of TCC channel, the D0 D star plus channel shows a very strong enhancement with the small source size, but for a larger source heavy-ion collision case, then we will see some kind of suppression as the LL formula predicts. And D0, D0, D bar 0 star case, it corresponds to the X3872 case. And we also have a strong enhancement for small size, but for large source size, then we expect the dip like this. And the couple channel threshold cusp appears in the case of D0, D0 star. But in the case of the DD star, then the threshold is too close, and we may not see the dip. And we have also checked that the small change of the potential, such as changing the range or the ISP independence, does not change the correlation function behavior significantly. Therefore, these results are at least a qualitative feature of this state will remain. And I hope that the data is measured. And I do not think that these correlation functions are well reproduced by, I mean that the data may not follow these predictions because the TCC, at least TCC is believed to be a tetraquark state. Hadronic molecule structure is assumed in making the potential, where the eigenmomentum is minus I over A0 scattering length. And in the weak binding relation, says that the scattering length is similar to the 1 over square root of 2 mu b. And this mu is reduced mass and b is binding energy. This kind of relation is expected for molecule. I mean that the wave function is fully described by the hadron-hadron wave function. Then, but what happens when the multiple state mixes? And in that case, the deviation from weak binding relation, this one, is we expect the deviation from this relation. And we can introduce the so-called compositeness X. X is a fraction where the wave function is exhausted by the hadronic molecule wave function. Therefore, 1 minus X is the multiple component, tetraquark or other component. If X goes to 1, then the weak binding relation is restored. But when X is 0, when the multiple state is dominant, then the scattering length will be much smaller than this this size. Therefore, when the multiple state becomes dominant, then this correlation function becomes much smaller than this one. Therefore, I hope that our prediction deviate from the data, and the multiple nature or tetraquark nature of TCC is confirmed by the correlation function data. Okay, that is our most recent work. Okay, and there are several homeworks to hadron physics from correlation function data. For example, the d pi correlation function prediction overestimates the correlation function data, which is a mystery because the interaction involving pion should be described by the just chiral symmetry. A leading order Weinberg-Tomozawa interaction, which is repulsive for this channel, and therefore the further repulsion may be necessary. But in these predictions, they use the lattice QCD data and extrapolate to these lattice data to the physical quark mass, and use those interactions to calculate, construct the pion d pi potential. I'm afraid that this extrapolation may fail. And by using the correlation function data, the hadron physicists need to reconstruct the d pi interaction again. Okay, it also applies to dk correlation function. Another homework to hadron and nuclear physics is the three-body correlation function. And their Alice collaboration also measures the PPP and their PP lambda correlation functions, which no theoretical operation exists. And I am asked by the Alice collaboration, but and I'm searching for several few body physics, but it's not yet obtained. And another one, phi p. And there's a phi p correlation function shows some strong enhancement, and there's a Alice collaboration extracted the scattering length of 0.85 plus I 0.116 centimeter, which contradict with the photo production data, which says that the scattering length absolute value is in the order of 0.1 centimeter. Therefore, there's a one order of magnitude difference for the photo production data and the correlation function data. And the lattice QCD result is larger than the correlation function measurement. This scattering length about 1.5 times larger than this one. Something is wrong. And we are working on this problem with the experimentalists. And in a few months, then we will have some answer of this. Okay, and in the last point, I'd like to mention that for the dynamical source, we have discussed it just as a Gaussian, static Gaussian source, but of course, it's desired to use the dynamical source, such as hydrodynamical calculation or something like that. But the situation is not very easy. For example, in the very famous review paper by Lisa Pratt, Schultz, Wiedemann in 2005, they say that in fact, all the model results that we review in the current subsection remain unsatisfactory with respect. They either deviate significantly from femtoscopic data, or they reproduce these data at the price of missing other important experimental information. Therefore, in 2005, we did not have any satisfactory framework. But later on, in 2009, Scott Pratt said that the here puzzle is shown to originate not from a single shortcoming of hydrodynamic models, but the combination of several effects such as the pre-thermalized acceleration using a stiffer equation state and adding viscosity. Therefore, by introducing all of these, then it may be possible to construct the dynamical model, which we can use also the flavored hadron pairs and correlation functions. And afterburner effects such as the hadron cascade need to be discussed. But at present, I do not know such kind of very reliable source functions for which can be used to calculate and predict the correlation function. Okay, let me summarize this talk. Okay, in this talk, Femtoscopy is useful to explore various hadron-hadron interactions only in this way. For example, the correlation functions of many pairs have been measured in these 7 years, 2015 to 2022. And some of the hadron-hadron interactions have been constrained, and source size dependence suggests the existence and non-existence of a bound state. And recent data start to explore charm-hadron interactions and three-body correlation, which are useful to extract further hadron physics information. And for more realistic estimate of hadron-hadron interactions, we need reliable interactions and the source models together with more data. And I think that it is, we are still in the first round, and which we can use the simple source and the existing interaction. And in the second round, I hope to use the dynamical source, and there's a directory extraction of the scattering amplitude from the correlation function in the second round. And third or fourth round, I hope that we go to the state of the art state of the correlation femtoscopic studies. That's all. Thank you very much for your attention. And I'd like to also thank my colleagues here, including some of the experimentalists. Okay, thank you very much.
Okay, thank you very much for very interesting talk. Actually, I learned a lot. Now it's open to questions, and please raise hand or please write chat comment. Is there anybody raising hand?
No.
There is a question by written question by Guo Zihui. You see in
yes. And first, Chairman Ko raised the hand. Please ask.
So you want me to ask first? Okay. Akira, nice to hear your talk. That was great.
Thank you very much.
Thank you so much. And I think I missed something. Can you show that slide on the source, the scattering length for the molecular state and the compact quark configurations? So your A naught, that equation, see that's right. A naught equal to R times 2x1 plus x.
Yes, and this one?
Yes, that's correct. The x is the fraction for the states to be hadronic molecule, right?
Yes, yes.
So if x equal to 1, A naught equal to R. So in the purely multi-quark state, x equal to 0. Therefore, R should be equal to 2R. A naught equal to 2R. So will that indicate larger scattering length in DD storm a signature? So I missed something.
Oh, when x is 1, then this factor becomes 1.
That's right. So that's molecular state. That's a good go to the first equation. A about A naught equal to R. So if the purely multi-quark state and x equal to 0, then A naught equal to twice of R. So then your conclusion should be larger scattering length in DD star can signal genuine tetraquark nature of PCC.
When x becomes 0, then this factor becomes 0.
Oh, it's 0.
A0 becomes 0.
Oh, sorry. It was out of my mind.
Okay. Therefore, in the case of the pure tetraquark state, which does not couple with DD or DD star, then there's no effect on the scattering length. Yes.
Yeah, that makes sense. Good. Yeah, thank you so much.
And also there is a written question on that. And does this correlation function has any relation with the correlation with the with the correlation function in quantum field theory, like correlating function of two colors? For this question, please just show the definition of C2 using using an operator. I think this is just sufficient. This is
therefore
N12 is observed two particle
observing
probability, and N1 and 2 actually this N1 and 2 are one particle observing probability and so on.
Yes, therefore it is at least not directly related to the correlation function of two currents in the quantum field theory. Yes.
Okay. There's another question from Li Shengen. Please ask.
Yes, this is Li Shengen from Beihang University. Ohnishi-san, thank you very much for your interesting talk. I have a probably technical or minor question. Can you go back to slide number 19?
19.
Yeah.
Yes. Okay.
No, yeah, 19. One more. Yeah, here. Here for this this small figure in the bottom right part. This one.
Which part?
Bottom, the right bottom one.
Old one? I'm sorry, I cannot see here.
Yeah, here, this, you see, you have 4 figures, right?
Yes.
The bottom one on the right.
Right.
Yeah, around the momentum around 250. If you see the data, that's small bump.
This one.
Yeah.
Yes.
Do you know what's the origin of this bump?
Lambda resonance, lambda 1520. That's
lambda 1520?
Yes, D-wave resonance.
Oh.
D-wave resonance cannot be described by this formula, and we have to extend the formula to include the P-wave, D-wave state in order to describe this bump. Bump or peak. And therefore we have separately introduced this resonance contribution.
So in your formula, in your calculation, you only considered S-wave interactions?
Yes, S-wave interaction and
D-wave, right?
That should be D-wave from the K minus P, yes.
Okay, thank you very much.
And there's another question from Zifi Guo.
Yes. Can you hear me?
Yes.
Okay. Can you go back to slide 9?
Slide 9?
Yes. I'm the person who wrote the questions about,
yes.
Because I'm a new person in this field. I would like to ask something.
Yes.
Slide 9. About the definition of the correlating function.
Yes.
Yes. So this N12 it means, what is the meaning of this N12 in the denominator?
This N12 is the 2-particle detection probability. Okay. And therefore 2-particle detection probability at the same time from the same event. And in that case, the quantum correlation, including the correlation from the final state interaction, exist. And N1 and N2 are the single particle probability and a single particle detection probability. And then when, how to say?
So it means, if there's no interaction, this C will be 1, right?
Becomes 1, yes.
Yeah, so in the second line, in my understanding, because you actually need to introduce this relative wave function between 2 particles. Actually, you use this, you give this relative function from the scattering amplitude, I think.
Yes,
but actually, you know that for 2-particle scattering, the scattering function as a scattering amplitude actually is a 4-point function.
Yes.
Actually, that means it actually it includes more information than this CQ, right? Because CQ is like a 2-point function. And to be more specific, in the scattering, actually, you also have for example, the left-hand cut singularity. But actually, if you only focus in the very near region, near the threshold, you use the effective range expansion. Actually, you throw away all the left-hand cut singularity. You only consider them like a point-like interactions. I don't know whether, because actually, as far as I know, there could be a problem because, for example, for the virtual states, or some people call it anti-bound state, and it's not easy to write down the wave functions. I don't know whether here, in your case, can you also, for example, measure this kind of But actually for the definition, I see that you can actually definitely measure, for example, even if there is an anti-bound state, you can even measure it. But as far as I know, that if you use the wave function to describe this anti-bound state, there can be problems. I don't know whether there are some solutions in this kind of language.
Anti-bound, when we go to the complex energy, then of course, when we have an anti-bound state and the complex energy, there will be a problem. But for the real energy, when we have an anti-bound state, we do not observe it in the real axis, for the real momentum axis. Therefore, we do not have for example, the divergence of the wave function, even if we have an anti-bound state. Therefore, for practical purposes, I think that it is not a problem. For example, in the case of the Guzai, P Guzai wave function scattering, then there is a virtual pole just below 4 MeV or 5 MeV below the threshold. But the wave function for calculation works very well, and the results are stable. Therefore, and anti-bound state is a kind of the pole in the other Riemann sheet.
Yes.
Do I have wait a minute? Do I have the I hope that I have some slide for the yes.
For the Riemann sheet?
Yes. This one I have to show. Anyway, let me go. And in the case of the P Xi minus scattering, then there is a so-called virtual pole around here, and but in the complex momentum space, then this virtual state is in the lower half plane. And the lower half plane contribution is small on the real axis, and we do not see it very well, especially in the real energy scattering. And anti-bound state, this corresponds to your definition of anti-bound state. Is it okay, or are you talking about different pole? Is it corresponds to close to your anti-bound state?
No, actually, I think this looks like a bound state, because it's if you have two virtual state poles in the complex plane, this corresponds to a virtual physical state, like. But actually, for one physical bound state, you must have one bound pole and another virtual pole. They are close to the threshold. Like I mean, in the N scattering, you have the deuteron in one channel, and the other, the atom-spin one channel, you have an anti-bound state, right?
And that's the virtual pole, yes.
Yes.
Dineutron has a virtual pole close to the threshold. Therefore, the phase shift goes up very quickly, and the correlation function is strongly enhanced in the case of dineutron. Okay. Therefore, I think that maybe this virtual state may be corresponding to your anti-bound state. I hope. If not, I'm sorry for that.
Okay, so thank you for your explanation. Okay.
Yes.
Okay, now there's a question from Nusu.
Yeah,
please ask.
Thank you for the nice talk. I have a question, maybe on the interpretation of the data. Could you go to slide 3?
Page 3?
Yes, your introductory slide. So you see in the center, you have these hadron-hadron interactions. Then
Yes.
most of the left, to me, it's like in a vacuum. And
Yes.
in case of a neutron star or in heavy
Yes.
ion collisions, we may be in a very high baryon density region.
Yes.
Are they uniformly can be treated similarly or not? My question actually is really, if we do measurement in PP collisions, for example, can we really apply those results to help us to understand the inner structure of neutron star? Because I think it's also related to page 9. How do you factorize your wave function and wave interaction and the wave function? It's related to that.
Okay. First, for the calculation of the equation state from based on the hadron-hadron interaction, then we have to start from hyperon-nucleon and hyperon-hyperon and nucleon-nucleon interaction. Then from hadron-hadron interactions to the equation state, there is a long way from vacuum to the finite density and for high density, but this is really a starting point. And for the actual calculation of the equation set, we also need 3-body interactions and 4-body interactions and so on, which is not known yet, but for example, the 3-body correlation may help. And I'm not sure, but they may help, and the finite nuclear calculation results, such as hypernuclear or nuclear binding energies, those are important. And then in a lucky case, we can reach the equation state from the YN and NN interactions. That is my hope. And for the equation state to the QCD phase diagram, that we also have a long way from here to here. But this is a kind of the bottom-up approach from hadronic matter to quark matter. And that is also necessary. But of course, the heavy ion collision can directly go to this higher density region. Therefore, the heavy ion collision have 2 ways to reach the QC phase diagram: directly to the high density region, and indirectly via the hadron-hadron interaction. And that's a good point for heavy ion physics, I hope. And page 9, and factorization of 2-body wave function to relative and center of mass. Is that the question? And yes, 2-body wave function is, of course, the center of mass motion for the 2 particles is assumed to be a plane wave. Then the absolute square of the center of mass wave function is just 1. Therefore, we can ignore the center of mass wave function from here to here. And the relative source function is defined as the normalized one, and the integrating out to the center of mass coordinate. Okay, then only the relative coordinate remains. That is the thing which I did from here to here. Center of mass variable integral out is the thing for the source function, and 2-body wave function is assumed to be the relative wave function times the center of mass wave function, which is assumed to be a plane wave.
But can you define asymptotic state in the case of matter? I mean, in matter, can you define asymptotic state?
Asymptotic matter?
No.
What do you mean?
In medium.
A dense medium, yes.
Okay. Yes.
You don't want to calculate correlation in the medium. As Akira mentioned, you want to extract hyperon nucleon interaction. From there, you develop based on the many-body theory, you get equation state.
Yes.
Nobody going to measure the 2-body correlate, the hyperon correlation in the mediums. That's not relevant.
That's right. Yes, we Yes, nobody discussed before, I think. But we assume that the scattering takes place in vacuum. Correlation is created in the final state interaction and the final state scattering. Therefore, in most cases, the scattering takes place in vacuum. That is the assumption, implicit assumption, which I did not explain. I'm sorry,
Right. Yeah.
Monsieur.
Well, the question is these interactions happened in